Hello, Martin, or Martin.
Hello.
Maybe I should call you Martin today.
Martin, yes, as you want.
So, second talk is, I never know how to pronounce it, whether in French I say RUM, but RUM is a cold that you get when it's when in the winter, so it's a RUM methodology.
RUM, yeah,
RUM.
exactly. By the way, everyone can see my screen?
We can see your screen. You already told me that we can record your talk. And so let's do it. Your turn,
okay.
Martin.
Thank you. Thank you. Thank you very much. Hello, and thanks to everyone for assisting to this talk. It's always joyful for me to present the work I'm interested on to such a nice audience. So the title of my talk is Aggregating Robustness, Uncertainty Quantification, and Monitoring Attributes for Trustworthy AI with the RUM methodology, which I'm going to try to explain in the span of 45 minutes. So I'm going to go and dive right into the plan of this talk. So I'm going to start with a general introduction, which in a way is going to be a 4-year retrospective of some of the work done within the Confiance AI program and some perspectives on the work done in its current sequence collective initiatives. And that will also serve as a motivation for why the need of this RUM methodology. Then I'm gonna get into the details of the methodology, its core themes, and I'm gonna just pick 2 focuses, like on specific topics related to robustness. Then I'm gonna go and explain into somehow into detail a method using tropical algebra for aggregating attributes that I'll be explaining in a bit, and at the end giving some conclusions and perspectives. So let's start with the general introduction, which is the first part of my talk. So the deployment of AI in critical systems imply at least 6 core attributes which are validity, transparency, and explainability. I'm not going to give you the full details of this because I'm going to concentrate only on one of them, but still I'm going to name at least like the types of them: security and robustness, dependability and safety, data and privacy governance, and accountability and responsibility. So these are the themes that we collectively worked on within this Confiance AI program, and which are also the core themes of the Atrass seminar. So the point is that all of this impacts the overall life cycle engineering, like all of its cycle, because we need new engineering methods and tools to support the life cycle of critical systems that are specifically AI based, and we need also new tools to ensure qualification and compliance with regulations and standards. So one of the things that we did in Confiance was to produce this end-to-end methodology that can be just reframed as a W cycle that you can see in here. And the part of evaluating and assessing trustworthiness, which is mandatory, in a way, I want you to focus in 3 of these 16 or 17, I never remember exactly, steps, which are to evaluate a trained ML model and its complementary software items, to evaluate an on-a-target hardware, and evaluate not an ML model, but an ML or actually an AI component, to be more precise. And I'm going to come to this at the last part of the talk. But first of all, I'd like to make a little, take a little time to make more specific what exactly we're evaluating, because all of this is an evaluation relative to what we have specified and architectured for an ML component or AI component. So how does this work? one of the conceptual outcomes of the Confiance AI program was that we have a model life cycle which goes through the usual steps of model selection, training, tuning, evaluation, and so on. But we came to the conclusion that there is no all-in-one model, not even among foundation models, that for critical tasks, but rather AI components made for an AI function and that are made out of a central model, which might be, for example, I'm going to give an example actually just after. There's a central model that performs this a principal task, this AI function, and auxiliary models that, for example, process inputs, provide enriched outputs, for instance, giving uncertainty quantification estimates, produce trustworthy metrics for monitoring, and so on. So the point is that these AI components are multimodal, and multifunctional, meaning that we are shifting from this paradigm of thinking that one model has to have has to equal to one functionality. So in Confiance AI, we developed a plethora of tools assembling functionalities to design and evaluate AI components that you can essentially represent this way. So you have inputs, a bunch of different tools to do pre-processing, tools to do inference either via pre-trained models, via retrained models, but in any case, afterwards you do some post-processing in order to get some enriched output. So this is a view of an ML component in development only. And here is an example of such a tool that we developed. So a test time OOD preprocessor for an object detector. So this is a library called Neural DE for Neural Domain Extension, which is a Confiance AI Python library, was deployed in production in one of our the partner companies and is available for various industrial use cases. So the idea is that simply you notice that you have a poor performance on original out-of-distribution input, which is on the left, simply because the object detector was trained by day, but is being tested by night. And you use a bunch of generative AI, but also monitoring modules in order to pre-process it so that you bring it back to its original distribution, which is the pre-processing essentially just takes the video that is in the left and takes it to the right, and you can see that a lot more bottles were actually counted that were not counted in the left. So this is just one example of one of these tools that we developed, and we developed dozens of them in Confiance AI. So this gives us motivation for the RUM methodology, because the take is that the auxiliary models designed for an AI component have a life cycle of their own, meaning that if we just focus for a second in robustness, uncertainty, and monitoring, they actually have a life cycle of their own, and then they will be put once they got matured enough, they will be then included in your AI component as these auxiliary models that I was talking about. So we needed a methodological framework describing what, when, and how to use such tools like a Neural DE. One, for designing complex AI components for an AI function, for analyzing and evaluating such components as indecomposable entities, and for organizing tailored trustworthiness trade-off metrics at the development phase. So this is the objective of that the RUM methodology tries to address. And the RUM methodology takes its name because currently it's focused on it's already a lot, I think, but robustness, UQ, and monitoring, hence the name. So that being said, let's get into the second part of this talk, which is a deep dive of this RUM methodology, and already start by saying what does it mean to have a methodology in here. So this methodology is part of the catalog of Confiance AI assets, and it's soon to be open sourced as a document. And it is the product of a collective effort of a lot of people, which are, you can see as contributors for it. It is a methodology that is supposed to evolve in time, so it is supposed to evolve in different versions, just as you update, for example, libraries. And since I cannot yet give you a complete, it is not yet open source, I can still show you the table of contents on how it works, and you can already see that it is a pretty long document that doesn't really work exactly just as a single research article. Yet, the whole point of this methodology is that we're going to try to, if I react to what Bertrand said just 10 minutes ago about scientists being pessimistic on what short-term developments we can do. In a way, this RUM methodology tries to also think conceptually a little bit with a step back on the tools, on the techniques that we use in order to know what we are trying to achieve. So let's start with one of the core themes of the RUM methodology, which is to actually produce these streamlines for robustness, uncertainty, and monitoring. So in a simplified version, it looks like this. So you have, for robustness, say, train time robustification techniques, which might be adversarial training or randomized smoothing, for example. There can be test time robustification methods that can be adversarial purification via diffusion models, say. Then once you develop them, you evaluate them as such, and then you plug them into your as subcomponents of your AI component. And there is a difference between evaluating the AI component and evaluating the component's robustness in a say global way, differently that how you evaluated a robustification protocol. And you have this the same kind of life cycles for uncertainty and monitoring. And the way for a while in Confiance that we dealt with these tools addressing each one these streamlines was to actually think of them as separate tools. This one tool is for robustness, another for UQ, another for monitoring, and we assess them as such. So we give an assessment of at the local level of this each one of these tools within their own life cycle. This does not take into account the operation of the system in which they sit, at least not immediately. And there is little interaction between robustness, UQ, and monitoring at this level. Essentially, when you develop adversarial training, you will evaluate it against adversarial attacks, but you are not, for example, producing any immediate insight into the way you're estimating uncertainty quantities or the way you're extracting KPIs to be monitored in your monitoring system. And the problem is that this simplified version that I just showed you actually does not correspond to what we actually had to handle, which actually looks like this. As you can see, it is much more complicated than this simplified version. We have a bunch of robustness evaluation techniques, intrinsic property testing, specification testing. Worst case in distribution, but in ODD, so operational design domain evaluation. Average case out of ODD evaluation, and so on. And you can also see that there are arrows going in many different ways. You can use, we had to handle attacks that really just target uncertainty estimators, I'm going to give an example of this. So you can see this, that in order to actually account for this, we needed to revise the way we analyze robustness UQ and M, and at least divide it in two. So on the right, you'll have on this green stack your usual robustness UQ and M evaluation of the AI component to address high-level trustworthiness attributes such as those that we saw at the beginning. And on the violet stack in here, which is what we like inside of the RUM methodology is considered to be an analysis, is evaluation of implemented RUM tools in their performance as RUM measures for an AI component, which means to address lower levels of attributes. So I'm going to get into a detail on what this means with concrete examples in a bit. But the fact of already having to think this separately brings the fact that in order to truly have an assessment that takes into account all of these interconnections that I just showed you, we needed to think it not only in terms of evaluation protocols or mitigation protocols, extraction methods, exploitation methods, but we needed to analyze a lot of things. We need to analyze our protocols, our estimation techniques. We need to also analyze the defenses in their actual capacity of defenses. But overall, what this means is to give it a functional assessment of at the system level on the impact of the operation to be rendered, the AI function, to analyze the way components interact within the system in which they sit. And in here, it's where we actually see the strong interactions between RU and M that appear. So I'm going to just give a focus on robustness. And essentially, as you saw already, this works at least in 4 different dimensions. So you have, for example, if you start from robustness evaluation protocols, the first question you're going to ask in analysis is the evaluation protocol reliable? And if not, you design richer or more better adapted evaluation protocols. From these evaluation protocols, you gain insight on how to design robustification approach, and then you evaluate along the same protocols to see if you actually gain something. But this is not the same as actually asking the other question, which is, okay, but will the defense actually stand after deployment? And if so, am I not making trade-offs? Typically, the accuracy and robustness trade-off that we see. Are we actually controlling it or accounting for it in this robustification method? And that is something that we cannot simply account in when we are evaluating, because it means that we change some optimization objective when we are, for example, making adversarial training. So the idea is that to ask the question, can we come with a systematic methodology to organize and assemble the usage? Sorry for the little typo. To assemble the usage of these confiance.ai tools. And the idea is that the available methods and protocols that we saw during this program range into length for chains of correspondences, and the different chains address different lower levels of attributes. So, for example, if you take, we were talking about adversarial robustness. I'm going to get into the details on it just in a moment. But you will have actually different sub-attributes, all of them being inside of the umbrella of robustness. And I'm going to spend more or less 20 minutes right now trying to explain to you why these sub-attributes matter and why we needed to actually address them in a separate and delicate manner. So let's start with worst case in distribution robustness analysis. So what does it mean? Let's start with, say, this third case. What it means is when you take it from the robustness evaluation protocol, this really means to transform a theoretical evaluation concept into an algorithmic protocol. For example, crafting the strongest available adversarial attacks over a test set realizes the idea of worst case in distribution analysis. But then you can ask, okay, how do I analyze this protocol? Which brings us to this fourth part. And this evaluates the extent that an implemented protocol addresses this high-level attribute. For instance, if the protocol uses weak adversarial attacks against a well-defended model, it will generate an overestimated robust accuracy due to a poor quality evaluation protocol rather than a poor defense mechanism. So it is something that needs to be debugged in a way at the level of the evaluation protocol rather than at the level of the defense mechanism. So let's talk about the defense mechanisms. So robustification methods, adversarial defenses, means to transfer evaluation insights into methods for improving its defining methods. In this particular example, adversarial training is crafted to improve a model's performance in the context of worst-case evaluation. You literally just, instead of training a model on inputs, you train them over the worst-case vicinities of such inputs that you find using adversarial attack techniques. And then you can ask yourself, okay, but is this defense, what can I say about this defense, right? Meaning I need to evaluate the extent to which a defense will stand on new situations. And the example here is that it is a fact that the strongest attacks do not make the strongest defense in adversarial training, meaning that you could think that, okay, very well, we can just take the hundreds of different adversarial attacks, like threat models that have appeared in the span of 10 years, and simply put them all inside of the adversarial training objective, meaning to train over all of these attacks. But actually, if you do this, and someone comes up with a new adversarial attack that was not seen during adversarial training, it is a fact that adversarial training will generalize very poorly to this kind of unseen attacks. So analysis here allows you to control the strength generalizability trade-off for this defense mechanism. And this is something that is different from the trade-off that I was talking about, which is accuracy and robustness. And here is how strong is the set of adversarial attacks that you use for adversarial training against the generalizability capacity of the defense mechanism produced by this algorithm. And so you see that there are at least these correspondences that can happen that are of length 4. So let's see how this works for a minimal example of an AI component. Okay, so we are going to take as a central models a semantic segmentation model and 2 auxiliary models. One post-processing that post-process outputs inform about the outputs uncertainties with the uncertainty quantification, and a monitoring system that will be out of distribution detection based on these very same UQ estimates. So the question is, what does worst case in distribution robustness analysis looks like for this particular AI component? And people came up with very strong attacks in this very specific case. So you say that you have a clean image, and what you will do is to attack not only you will have a multi-objective function that will essentially abnormally target an uncertainty estimate for a model F at this particular input. And for instance, you can make it be underconfident, meaning that he's gonna say the model UQ model is gonna say I don't know when it shouldn't, when it should say I actually do know. And on the contrary, you can make it say that I don't know when it actually should. So it's going to become overconfident, right? And people have come with recent attacks. For example, two attacks in here that are minimum variance attacks and UST, which are these two attacks in here. I prefer instead of just giving you the technique to show you what they do to the AI component. On the first case, you can see that the segmentation is a little bit damaged, but not that much. Say the segment corresponding to this bicycle is still there. But then epistemic and aleatoric uncertainties are damaged. And for this second attack, you actually damage everyone, not only the UQ model, but also the central model. And the question is, does this extend to these other streamlines? Because this is, you can say, okay, we're starting an evaluation protocol that is starting on the robustness streamline, right? Well, actually, they do extend to these other streamlines because indeed, these very small noises can cause large overconfidence for these very same two attacks. You can make a model to maintain its accuracy, which is in blue, while absolutely make its uncertainty estimates unreliable, or actually damage both. And the whole point is that, okay, your model, you cannot really rely on it if what by reliance you mean having a reliable UQ estimator. And since we just decided that we were going to produce out of distribution detection using these uncertainty quantities, what happens is that large overconfidence causes large performance drops on this. Excuse me, there's another type here. It's OOD, out of distribution detection. So essentially, for very, very, very little noise perturbation amplitudes, all of the samples that were supposed to be flagged as out of distribution are not going to be flagged at all. At the same time that the model is going to become overconfident, and at the same time that the model is also going that the semantic segmentator will produce to you a completely wrong segmentation. So you can say, okay, but this is what happens if, for example, we change our, in here I didn't actually get into the details on what kind of UQ model we were using. Actually, it's ensemble kind of methods. But you can also ask okay, but let's say that you use conformal prediction. Now, the problem is that adversarial attacks violate the so-called exchangeability condition, which is the condition which makes conformal prediction to work, which means that adversarial attacks are very effective against conformal prediction. And adversarial defenses that control the prediction set size in conformal prediction have only been found recently. And essentially, what we're going to have is a trade-off that I'm going to explain later, that in this particular paper, they will try to mitigate and for them to be able to know that they actually mitigated, they produced an evaluation protocol that is strong, meaning that it consists on these so-called UQ-aware adversarial attacks that we were just seeing before, that are just these multi-objective adversarial attacks. So wrapping it up, coming back to these chains of correspondences, you have two different things. On one side, what you have is evaluation analysis as worst case in distribution robustness, protocols being multi-objective adversarial attacks, and aggregating impact over a span of scenarios, from which, for example, the attacker has white box only to the central model, which is different that when it has access to the whole AI component, and also increasing computational power. I mean, stronger attacks also are more expensive. And on the side of trade-offs, you have a trade-off between gain in adversarial robustness from adversarial training, but lost in efficiency in UQ produced by these lengthy conformal prediction sets that are overly unconfident, say. So this is for worst case in distribution robustness analysis. And if you switch to the to thinking, okay, but this is only adversarial robustness, and we also care about like a usual out of distribution robustness, let's just set some like methodological points, which are that adversarial attacks do not address the same as things like distribution shifts or common corruptions. On the one hand, adversarial attacks are formalized with an actual formalized optimization objective to be imperceptible either to human perception or detection mechanism. They exploit the neural networks architectures, and they maximize the damaging performance, meaning they serve, as we said before, as worst case in distribution analysis for network or AI component robustness. On the other hand, things like common corruptions, they are not formalized. They occur in real-world scenarios, such as meteorological changes, digital equipment changes, bad quality data. They are human-centered. You can detect them. You can very well see snow happening in one of these images. Can only be simulated. There is no such a thing as formalizing snow. And incurring to realistic damage because they happen also in ways that are not foreseeable, even when we already thought, okay, there is going, even if there is going to be rain, I didn't know that we were going to have this particular kind of rain in this particular kind of angle at this particular moment of the day, say. But the point is that it serves as average case out of distribution analysis for network or AI component robustness. And this distinction is very important because you don't want to mix them. And if you mix them, you need to give to come up with a scenario in where you actually are doing something that corresponds to reality. But before all of that, you can also ask me a question, which is, wait a minute, in the era of foundation models, is out of distribution robustness still an AI challenge? And the answer is yes. Foundation models do not solve domain generalization, and existing evaluation methodologies suffer from biases such as unrealistic hypotheses and data leakage. Very concretely, CLIP does not generalize across domains if evaluated correctly. And this is something that it took researchers about 2 years to actually understand, meaning that we had poor understood assumptions that led to scope of validity of empirical phenomena to be poorly defined. Concretely, CLIP appeared to be robust when evaluated in certain OOD evaluation sets, but actually these were already in some sense inside of CLIP's training set, and it took only a little filter to take out all this data leakage to actually realize that whatever domain generalization abilities that we thought were also, as this very popular paper said, a mirage, and actually do not happen. The clip turns to be not robust to this kind of, like in the sense of domain generalization. And if you always also see about another example, like you focus on OOD robustness to spurious correlations, namely correlations that do not imply causations in statistics, like you train a model to distinguish if you have a water bird or a land bird, and you think that the model is doing great until you put a water bird in a land background, and suddenly your model starts to perform bad simply because it picked up the land, like the background, as a part of the features of a water bird or a land bird, which is exactly what the spurious correlations are. But the problem here is that suppose that you have a bunch of methods to mitigate spurious correlations, and you actually have two benchmarks, waterbirds and Nico++, that propose to evaluate and rank different methods in their ability to mitigate spurious correlations. And the point is that if you can see in here, for example, if you take in order the benchmark, like the leaderboard of water birds, and then you take the same techniques and then you evaluate them and benchmark them on a Nico++, both of them are supposed to be standards for benchmarking mitigation proposals for spurious correlation. You can see that it resembles as nothing more than a random shuffle. So this is a problem, right? Because it means that we're not understanding a bunch of assumptions. So the take here is that it's crucial to adhere to an inductive philosophy to induce modeling hypothesis tailored on your use case. Is this benchmark of spurious correlations actually valid in or compatible to what I have as kinds of spurious correlations, rather than deducing models based on possibly invalid hypotheses. So you have two outcomes in this kind of analysis, which is validity measured by technical desiderata that I don't want to enter in here, but also ODD coverage, meaning that you only care about out-of-distribution data that is included in the specified operational design domain of your AI component. So this brings us to this last brick that I just presented a little bit before for this kind of methodological framework that we proposed with the RUM methodology. Now, I'm going to enter into the third part of this talk, which is that, okay, we see that there is a lot of problems, that there is going to be a lot of attributes, a lot of ways to evaluate, possibly disagreeing, and we needed to find ways of handling all of these lower level and fine-grained attributes, right? And this is a joint work with Juliette Mathioli, Carl Quintero, Henri Soyer, and Luca Matelli. It was presented in AAAI 2024.
Martin, can you do this in 10 minutes so that we have time for questions and discussion?
Yeah, that's fine. So, very fast forward, what we did in Confiance AI for Trustworthiness Assessment is to propose 4 steps. First step is to define trustworthy characteristics such as accuracy, correctness, and so on. And this part of the job was done. A second part of the job was to structure the problem into a knowledge graph of trustworthiness attributes. In here, you're gonna cluster characteristics to meta attributes into a semantic tree. And then you have two other steps, which is to handle commensurability and assess AI trustworthiness via multi-criteria aggregation, which is what I am going to focus right now. So first, for step 3, certain methods exist for reliability, accuracy, data quality metrics. Methods exist. For other attributes, we propose, such as the RUM methodology, our own methodologies to be able to assess and identify these KPIs. But once we do this, we can present them as in a visual representation way, as a radar chart way. But at some point, we will want to aggregate them and decide what is important, what is not, among all of these criteria, and being able to produce scores that account for them. So if I put all of this together, like this 4 steps methodology, the length 4 sequences, and this horribly complicated diagram for the streamlines that I presented, the RUM methodology brings fine rank sub-attributes at the interplay of deal-breaker requirements, typical in system engineering, but also optimization objectives, which are ubiquitous in AI systems or AI, ML models. And both are crucial when specifying and validating AI components. So we have a problem of aggregation based on weighted averaging. Why? Classical weighted averaging struggles avoiding unnatural trade-offs, meaning dangerous lacks in fine-grained robustness sub-attributes can still be compensated by good performance elsewhere. And they can also struggle capturing must-have criteria in a mix of requirements and optimization objectives. They might be easily just averaged out in all of this mix. So the idea is to leverage tropical algebra to handle these attributes. And for 5 little minutes, I'm going to get a little bit more technical to just make a little overview on what is this tropical algebra. It essentially consists on 2 kinds of algebras, which are actually semirings, that are called this max plus algebra or min plus algebra. The underlying set is going to be, say, let's only take a max plus. Is going to be the real line extended by a single element that you're simply going to symbolize as minus infinity. And the addition and multiplication operations are going to be changed. Sum operation is going to be the max operator, and the multiplication operator is going to be your usual sum. So it is a bit of a flex when it's the first time that you think of this. But if you simply formally define the sum and multiplication as max and plus, and you check all the semi-ring formal properties, associativity, commutativity, distributivity, and so on, you will find that they are semi-rings, and they are not rings simply because for max there is no such a thing as an inverse. Simply put, there is no element for which the maximum of A and B is going to be minus infinity, or simply put. We can come back to this in the questions if you want. The point is that the tropical algebra aggregator will be defined in the same way in here, as meaning as an average weighted sum, in where here J is going to represent one of these 6 macro attributes that I presented at the beginning of my talk, and I one of these respective atomic per attribute KPIs, such as those that I started to present with the RUM methodology. And the important part is the specification of the weights here depend on the operational design domain, which captures the applicative importance and dependency between these attributes. So, for example, if you take J to be robustness, and you just think about robustness only, then the aggregator only will read as, like the average sum will simply be the minimum of sums. in this case, or the maximum of different sums. So very concretely, in a toy example, it looks like this. If you take in here this mu1, mu2, mu_n as being accuracy under no attack or weak adversarial attacks, stronger adversarial attacks, patch attacks, which can be thought of kind of realistic worst case, but also environmental perturbations. I mean, these things are becoming like the kind of scenarios in where these things appear is becoming ubiquitous in LLMs safety with jailbreaks, or simply environmental perturbations such as blurring. So the take is to leverage RUM's insight in testing scenarios and map them to weight configurations, meaning that in a first scenario where you want to, for example, understand the worst case in distribution robustness, you will focus on the strongest possible adversarial attack within the distribution, which is here PGD. So you simply will single it out. And when you're computing the minimum of the different sums of the different arguments, you will come to some number. And you can have two other scenarios. For example, you do average case out of distribution robustness that we just explained before. You will want to target, for example, the very last kind of perturbation. So the mu5, you're going to give it more importance to this one. And you will have another kind of score. But you can also do the same for a third case, which is you can think of patches as worst case inside of the ODD robustness for deployment, meaning it is worst case, but yet it is in the ODD. The system is supposed to be able to handle patch attacks, and you get a score depending on the importance you give it to this scenario. So wrapping it up, tropical algebra has the potential for fine-grained and hierarchical trustworthiness aggregation, can handle both smooth and critical trade-offs where when usual weighted averaging usually concentrates on smooth trade-offs, and can efficiently single out requirements or deal breakers via the max or the mean operator while remaining sensitive to secondary criteria. And we have the perspective to leverage these with expert knowledge of communities such as system engineering, VNV, standardization for principal choices of weights at the AI component level, meaning not this toy case. So just to give a conclusion for the whole talk, the RUM methodology's current main objective right now is to go essentially from the left in here to the right in here, meaning it allows us to define more rigorously what the perimeter of an AI component is, starting from the fact that we have an automated feature, a system design and architecture, ML component requirements, AI component requirements, a specified ODD, key trustworthy indicators, meaning everything that is done in the first part of the W cycle, and little by little produce to you an ML component, at least in its current form, that addresses monitoring, uncertainty quantification, and robustness. And future avenues for this would be to extend this methodology to one for refining trade-off choices at specification level already, for usage of AI components during deployment, because all of this that I told you is yet a completely different story when AI components are deployed. And also integrating other streamlines that can appear, such as explainability streamlines or embeddability ones, hybridization ones, and so on. So with this, I think I'm going to stop here. So thank you very much for your attention.
Thank you, Martin. Thank you. I think you have shown also a lot of material with very interesting and complementary views about the subject. For the moment, I haven't seen questions in the chat, and I don't see any hand raised. I'm not going to ask you the same question as I did to Shuang first, but maybe you can give you could give some highlights or also ideas on what are the tools or tool chains that support the methodology at the moment?
The tools, you mean?
Software tools.
Okay, so that's the whole point. Yeah, this is a very important question indeed, because the whole point of the RUM methodology is not to be a tool, but to describe a holistic methodological framework to describe how to use tools. Like, what tools are you going to use, adversarial training or not, as implemented in this Confiance AI tool used. Conformal prediction, for example, on the top of my head, used as in the Punk library that was produced in Confiance AI. Or are you going to use preprocessing, such as a Neural DE tool? So it is rather something that is supposed to tell you how to use these tools in a way.
Yes, for sure. But what I would expect
there is
that you give an example of tool chain that has been tested, at least for in the framework of the methodology.
Of course. So in the first thing that I could say is that at some point during the very end of the Confiance AI program, we put a lot of effort into applying this end-to-end methodology to use cases. And at some point, the people trying to implement this end-to-end methodology had to come up with a very specific AI components to address their use cases. And from all of the engineers that applied this methodology, that asked for a RUM assessment of the evaluation of what they were actually doing, I can tell you that all of them radically changed at least one of their conclusions based on the insight that we addressed with the RUM methodology, meaning that before the RUM methodology, they had drawn a certain number of conclusions on how well adapted and how they used specific Confiance tools for crafting or evaluating these AI components. And after RUM, at least one, for some of them several, but for all that asked for a RUM assessment, at least one dimension got radically changed, either at the moment of designing the architecture of the AI component or at the moment of evaluating it. So this, sadly, indeed, is inside of this document that is going to be soon released. But in the meanwhile, you'll have to take me by my word, but the details are inside of this methodology, of course.
So maybe at the next Atrass in 1 month, if you have published the document before, we will ask the audience we will ask them questions about the content of the document to see if they have to check if they have read it entirely. Just joking. I don't see any question. So that was so clear that everyone is happy. In such a case, I think it's time to thank you for the presentation.